We tend to talk about artificial intelligence as if it's spreading evenly, like it's moving across the economy in one smooth, continuous way, showing up everywhere at once. But when you look at where it's actually taking hold in the physical world, not in software, but in real environments, the pattern looks very different. It doesn't move uniformly. It shows up in clusters. And that distribution starts to tell a more precise story. Because it suggests the limiting factor isn't just the technology itself. It's where the real world can support it.
That's where the conversation usually drifts off course. We've focused so heavily on improving the models, making them faster, more capable, more general, that it's easy to assume intelligence is the primary constraint. But once those systems leave controlled digital settings and interact with physical environments, the constraint shifts. It's no longer just about what the system can process, it's about the environment it's operating inside. Because the physical world isn't consistent. Some parts are tightly organized, repeatable, measured, highly controlled, and others aren't. They change constantly, they introduce variation, they resist standardization. And those differences matter because machine systems don't engage with all environments equally. They settle where the surrounding structure already supports them.
So instead of expanding outward in every direction, they're finding specific points where they can actually take hold.
Exactly. And you can see that clearly in industrial robotics. We're deploying hundreds of thousands of units each year globally. The scale is significant. But what stands out isn't just how many systems are being deployed, it's where that deployment concentrates. A large share sits within a relatively small number of regions, particularly in East Asia. Not because the technology is limited geographically, but because those environments are already built to support it. Highly coordinated manufacturing systems, standardized workflows, tight tolerances, reliable inputs. In those settings, machine intelligence can translate into consistent physical action.
So the technology isn't reshaping reality on its own. It's stepping into environments that have already been shaped.
That's the key distinction. These systems don't organize the physical world from scratch. They amplify environments that have already been organized. And that shifts where the real constraint sits. Because it's no longer just about how capable the system is, it's about how much of the environment has been prepared in advance. And that preparation takes time. It requires infrastructure, coordination and control over variables that are often difficult to stabilize in real-world settings.
Which helps explain why you can see strong growth in specific areas, like robotics adoption accelerating in parts of North America, without seeing that same transformation spread across everything.
Right. You can have rapid progress within a narrow range of environments without that translating into broad change across the entire physical economy. Because once you move outside those environments, the stability starts to break down. Inputs become less consistent. Timing becomes harder to control. Outcomes become less predictable, and the system no longer behaves the same way. So what looks like a general wave of adoption is often a much more selective pattern up close.
Which changes how you read the progress. It's not simply that better systems lead to universal adoption. It's that better systems deepen in places that are already compatible with them.
Exactly. And that's the boundary condition for everything we're about to explore. Intelligence can scale quickly. We've seen that. But the physical world doesn't move at the same pace. It has inertia, it carries constraints, it's shaped by infrastructure, coordination, and legacy systems that take time to change. So what you end up with is an uneven alignment. Highly capable intelligence, interacting with environments that only support it in certain pockets.
So when people talk about AI transforming the physical world, the more precise version is that it transforms the parts of the world that are already prepared for it.
That's right. It's not a question of whether the technology works, it's a question of where it can work reliably. And in many cases, that depends less on the system and more on the environment it enters.
Which shifts the framing completely. Because now the question isn't just what these systems are capable of, it's where that capability actually holds.
And once you start looking at it that way, a consistent pattern begins to emerge. The environments where these systems perform best aren't the ones that demand the most intelligence. They're the ones that require the least variation.
If these systems aren't spreading evenly across the physical world, and instead appearing in specific types of environments, then the more useful question is what those environments share. Because on the surface, they don't look concentrated. Warehouses, production lines, distribution networks, different industries, different functions. But when you look more closely, the pattern underneath them is consistent.
And that pattern isn't primarily about intelligence, it's about stability. These are environments where variability has already been reduced, processes are defined, movements repeat, inputs arrive in predictable forms, which means the system isn't encountering a new situation each time it operates. It's working within patterns that hold over time.
So the advantage comes less from handling a wide range of scenarios and more from operating inside a narrow range with high precision.
Exactly. That's why you see strong performance in areas like warehouse automation. Not because the tasks are especially complex, but because they're structured. Items move between known points. Sorting follows defined paths. Timing can be coordinated. And once that structure is in place, the system can deliver measurable gains, higher throughput, fewer errors, more predictable flow.
So the system isn't broadly reshaping work, it's reinforcing a specific type of workflow.
That's right. Performance improves because the surrounding process has already been shaped to support it. And once that alignment exists, it becomes scalable, which is why deployment tends to follow a consistent path. Start in the most controlled settings, establish reliability, then extend outward gradually.
So what looks like broad progress is often concentrated success.
Yes. And that concentration matters, because outside of those structured environments, the same systems don't behave the same way. Inputs become less predictable, timing becomes harder to coordinate, outcomes vary more, and performance starts to degrade.
Alright, Sophie, let's start with performance. Most of the conversation focuses on systems becoming more capable. But how much of that is actually coming from the system itself versus the conditions it's operating in?
In practice, it's both, but the second part is often underemphasized. What appears as increasing capability is frequently the result of better alignment between the system and its surroundings. The goal in these environments isn't broad adaptability, it's reliable output at scale. You're not trying to build something that can handle any possible situation. You're trying to produce the same result repeatedly with minimal deviation. And the most effective way to do that isn't infinite flexibility. It's reducing what needs to be interpreted in the first place. So instead of exposing the system to a wide range of inputs, you narrow that range. Once the variability is reduced, the system can operate more consistently and the performance improves.
Right, so a lot of what looks like intelligence is actually happening before the system even runs, even just in how the environment is designed. How much of the performance is really coming from that layer?
A significant portion of it, because preparation changes the nature of the problem entirely. Paths are defined in advance, inputs are standardized, Decision points are constrained. Instead of asking the system to resolve ambiguity in real time, you remove much of that ambiguity ahead of time. So the system isn't navigating an open-ended environment. It's operating within a structure that has been designed to support a specific outcome. That's why these systems can perform so well. They're not solving a general problem, they're executing a highly constrained one.
Yeah, that makes sense. So the system is executing, but the environment is doing a lot of the heavy lifting. Does that mean the environment is effectively carrying a part of the intelligence?
In many cases, yes, the environment absorbs uncertainty in advance. Instead of presenting a wide range of possible situations, it limits the number of scenarios the system has to deal with. And when that's combined with repetition, continuous cycles of the same operation, small improvements become meaningful. You reduce wasted motion, you improve coordination, you lower error rates, and those gains compound over time.
Right, and that's where it starts to feel extremely efficient, but also a bit fragile. What's actually happening when something falls outside that structure?
That's where the limitations become visible. These environments are built around specific assumptions. When those assumptions hold, performance is very strong, but when they don't, the system doesn't always adapt smoothly. It may slow down, pause, or escalate to human intervention, because outside that predefined structure, it doesn't have the same level of certainty. So the efficiency is tied to a narrower operating range.
Got it. So it's not a hard failure, it's more like a system losing its footing for a moment. What is it about less structured environments that makes it so difficult?
These systems are designed around continuity, steady, predictable flow. When that flow is disrupted, the system has to resolve the disruption before it can continue. In highly controlled settings, those disruptions are rare, but as you move into less structured environments, they become more frequent and more varied. And that introduces friction, not because the system stops working entirely, but because it encounters more situations it wasn't optimized to handle smoothly.
Right, so from the outside it can look like rapid adoption, but underneath it's actually quite concentrated. Is that the main reason why the growth appears much broader than it actually is?
It is. A relatively small number of highly structured environments can generate a large share of the visible success. And because those environments operate at scale, they create the impression that the transformation is happening everywhere. But when you look more closely, adoption is still uneven. The systems are becoming more embedded, more efficient, more capable within those environments, but they're not spreading uniformly across all settings.
Right, so acceleration doesn't necessarily mean expansion. It might just mean going deeper in places where things already work. Why does that tend to happen first?
Systems tend to deepen first. They become more integrated, more reliable, more central within environments that already support them. Only after that do they begin to extend outward. And even then, the expansion follows the same pattern, moving step by step at areas that can be gradually stabilized. Because outside those conditions, the problem changes. The system is no longer operating with the same level of support.
So when you step back and look at the pattern, these systems aren't appearing where the problems are most complex. They're appearing where the surrounding conditions are most stable.
And that reframes how progress shows up in the physical world. We tend to associate intelligence with handling complexity. But in these environments, the value often comes from reducing it, from shaping the process so the same task can be performed repeatedly with minimal variation.
Which means the breakthrough isn't isolated to the system itself. It's shared with the environment it operates in.
Exactly. Performance comes from alignment. The task is clearly defined, inputs are controlled, outcomes are measurable, and the system can operate within that loop continuously. But as that structure loosens, predictability declines.
So what looks like intelligence in action is often the result of stability in action.
That's right. And that's why these systems scale the way they do. They don't expand everywhere at once. They deepen within environments that already support that stability, coming faster, more reliable, more embedded over time.
Which makes the boundary of that expansion especially important. Because it isn't defined by theoretical capacity, it's defined by what the environment can sustain.
Yes, and beyond that boundary, the challenge shifts, not performance, but fragility. As variability increases, assumptions begin to break, and the system encounters situations it wasn't designed to handle smoothly.
Which leads directly into the next question. What happens when those conditions no longer hold?
Exactly, because in the physical world, it's not the average case that defines the system, it's the exceptions.
High-interest debt can feel like a trap. With Volo, you can break free. Just choose how much you need. Set the terms that work for you. Share your story. And send the request to people you trust. Your network sees it instantly, and you're on your way. Borrow with confidence, at fair rates, from people who believe in you. Join the waitlist today at voloapp.ca.
If the previous segment focused on where these systems perform well, this is where the picture starts to shift. Because those environments are intentionally controlled. They're designed to reduce variability, to keep outcomes predictable. But outside of those environments, the physical world behaves very differently. Conditions change, inputs vary, timing becomes less precise. And that changes the nature of the problem.
It does. Inside controlled environments, the objective is consistency. You define the process, stabilize the inputs, and repeat the operation. But outside of those settings, variability becomes unavoidable, and variability introduces a different kind of challenge, not just reduced performance, but the possibility of being wrong in ways that carry consequences.
So it's not just that the system becomes less effective, it's that the cost of error increases.
Exactly. And that's a key distinction between digital systems and physical ones. In software, errors are often recoverable. You can rerun a process, roll back a change, correct the output after the fact. But in physical systems, the system is acting on real materials in real time. So when something goes wrong, it doesn't just produce a bad result. It produces an outcome that has already taken effect.
Which changes how you evaluate performance.
It does, because it's no longer defined by how often the system is correct. It's defined by what happens when it isn't. Even if those moments are infrequent, they carry disproportionate weight. They're the situations where the environment doesn't match the pattern the system expects, and those situations shape how the system is perceived and trusted.
So averages stop being the right way to think about performance.
Not in the same way. These systems often operate within tight tolerances, small margins in space, time, and coordination. And at that level, small deviations don't remain isolated. They propagate, they compound, they become costly quickly, which means performance isn't judged by how well the system handles the normal case, but by how it handles the exceptions.
All right, Sophie. So if that's the shift, does that mean that these systems are ultimately judged less on their strengths and more on how they behave when something goes wrong?
In many cases, yes. In controlled environments, you can focus on optimizing performance, speed, accuracy, consistency. And those improvements are meaningful because the surrounding conditions are stable. But once you move into more variable settings, performance alone isn't enough. What starts to matter more is how the system responds when it encounters something it doesn't fully understand. Those situations aren't constant, but they're inevitable. You can have long stretches where everything works as expected, and then suddenly encounter a scenario that doesn't fit the pattern at all. And in those moments, the system isn't being evaluated on its average performance. It's being evaluated on how it handles uncertainty.
Right. So even if these moments are rare, they end up defining the system. Is that because the impact of those failures is so much higher?
Exactly. The impact isn't evenly distributed. A system can perform correctly most of the time, but if the situations where it fails are the ones that carry real consequences, delays, damage, safety risks, those failures become the defining feature. Because the real world doesn't respond to averages, it responds to outcomes. So even a small percentage of failures can outweigh a large number of successful operations, depending on where those failures occur and what they affect.
Yeah, that makes sense. And that's where it starts to feel very different from software, right? What fundamentally changes when you move from digital systems into physical ones?
The feedback loop changes. In digital systems, the output is information. If something goes wrong, you can often correct it after the fact without lasting impact. But in physical systems, the output is action. The system is interacting with the world in real time, moving objects, coordinating timing, affecting physical states. So when an error occurs, the consequence has already happened. Something has been misplaced, something has been delayed, something has been damaged, and at that point, you're no longer correcting a result. You're managing the consequence of that result.
So errors don't stay contained. Is that what causes small deviations to escalate so quickly?
Yes, especially in systems that operate within tight tolerances. In manufacturing, small physical deviations can affect the integrity of the output. In logistics, small timing disruptions can cascade through the system. What begins as a minor inconsistency at one point can propagate across multiple stages. And once that propagation starts, it becomes difficult to isolate and contain. That's why variability becomes such a central challenge. Not because it's constant, but because when it appears, it can spread.
Right. And that makes those headline accuracy numbers feel incomplete. How should we actually interpret something like 98% accuracy in this context?
Those numbers tell you how often the system is correct, but not how it fails. If the failures are low impact and evenly distributed, the system can still function reliably. But if the failures tend to occur in more complex or less predictable situations, they become much harder to manage. So the question shifts from overall accuracy to failure behavior. Where do the errors happen? What conditions trigger them? And what happens when they occur? Because those factors determine whether the system can operate safely and reliably at scale.
So when the system reaches one of those edge cases, what does it actually do in that moment?
In most cases, it doesn't push through. Well-designed systems are built to recognize when they no longer have a high-confidence path forward. At that point, they pause, flag the issue, or escalate. And that escalation is where the human layer becomes critical. A person can interpret context, recognize that something is unusual, and decide how to respond in a way that the system cannot. So rather than eliminating uncertainty, the system is designed to operate up to a boundary and then hand off when that boundary is reached.
Got it. So even in highly automated systems, there's still a built-in backstop. Is that human layer essentially unavoidable as these systems scale?
Yes, because the system is highly effective within the range of situations it understands. But outside that range, it doesn't have the same flexibility. And as the system scales, it encounters a wider variety of conditions, different environments, different edge cases, different forms of variability. That increased exposure makes those edge cases more visible over time. So scaling doesn't just increase output, it increases the system's interaction with uncertainty. And that's why the human layer remains essential, not as the primary operator, but as the mechanism that absorbs what the system cannot resolve.
So the picture that starts to come into focus is different from how this is usually framed. It's not just about how often the system is correct, it's about how it behaves when things don't go as expected. Because in physical environments, those moments carry disproportionate weight. And they shape how the system is ultimately judged.
Exactly. In controlled settings, uncertainty can be reduced and contained, which allows performance to be optimized around repeatability and precision. But once you move into more open environments, those moments can't be eliminated. They can only be anticipated and managed. And that's where fragility emerges. Not as constant failure, but as sensitivity to forms of variation that are difficult to predict and even harder to absorb once they occur. Because, unlike software, where errors can often be corrected after the fact, physical systems operate in real time, and their outputs have already taken effect, which means the threshold for acceptable error becomes much lower, and the consequences of failure become much more immediate. Which means the system has to be designed not just for performance, but for failure. It has to account for the fact that it will encounter situations it doesn't fully understand and define how it responds when that happens, whether it pauses, escalates, or hands off control. And that's where the idea of autonomy starts to shift, because in most real-world systems, autonomy isn't absolute, it's distributed. The machine handles the predictable conditions it was designed for, and the human remains responsible for the situations that fall outside that range. So the system doesn't eliminate uncertainty, it reorganizes how uncertainty is managed.
Your money can do more than sit in a savings account. Browse real requests from your trusted network. See the repayment plan and the return. Fund it in seconds and start earning passive income. Lend with purpose. Put your money to work, right where it matters. Join the waitlist today at voloapp.ca.
If you follow the thread from the last segment, the picture starts to shift again. Because the assumption around automation is usually framed as removal. The system improves, the human steps back, and over time disappears from the process entirely. But that's not what these systems actually look like in practice. What you see instead is redistribution of responsibility, a reorganization of where different types of work sit inside the system.
Exactly. The machine takes on the parts of the process that are stable, the repeatable work, the predictable flows, but that doesn't eliminate the rest of the system. It separates it. What remains are the situations where those patterns stop holding, the moments where the system doesn't have enough clarity to proceed with confidence, and those moments don't disappear as the system improves. They become more concentrated.
So instead of the human sitting at the center of the process, they move closer to the edge of it.
That's right. They're no longer executing every step, but they remain essential to the system functioning because they're the ones handling ambiguity, interpreting situations that fall outside predefined patterns, making decisions when the system reaches its limits. And that creates a different kind of relationship between human and machine. Not operator and tool, but a layered system where each part is responsible for a different type of problem.
Which shifts the framing again. Because now the question isn't just how autonomous the system is, it's how that autonomy is structured.
Most real-world deployments aren't defined by full autonomy. They're defined by assisted autonomy, systems that are highly capable within a defined range but still depend on human intervention to remain reliable outside of it. And in many cases, that human layer isn't optional, it's built into the system itself. What tends to happen is not removal but concentration. As systems improve, they take over the parts of the work that are stable, where inputs are consistent, outcomes are predictable, and the environment behaves in ways that can be mapped in advance, and they tend to handle those parts extremely well. But that doesn't eliminate the rest of the work. It isolates it. What remains are the situations that don't fit cleanly into those patterns. Ambiguous cases, borderline conditions, moments where there isn't enough clarity to proceed with confidence. And those moments don't disappear as the system scales. They become more visible. So instead of human effort being spread across the entire process, it gets pulled toward those specific points. Less frequent, but more demanding when they occur.
Right, so instead of being inside of the flow of the work, you're positioned just outside of it. What does that role actually feel like day to day?
It shifts from continuous execution to intermittent judgment. You're no longer carrying the process forward step by step. Most of the time, the system is moving on its own. Your responsibility is to recognize when that movement can't continue and understand why. And those moments don't arrive in a steady rhythm. You can go long stretches where nothing requires attention, and then suddenly you're pulled into a situation that demands a decision, often with limited context and very little time to orient yourself. So the work becomes less about doing and more about maintaining proximity, staying close enough to the process that you can re-enter it effectively when needed.
Yeah, that sounds deceptively difficult because you're not continuously engaged, but when something happens, you have to respond immediately. Is that where most of the cognitive load actually sits?
That's exactly where it shifts. When someone is actively performing a task, there's a natural rhythm. You receive constant feedback. You make incremental adjustments. You remain embedded in the context. In a monitoring role, that rhythm disappears. You're holding context over time without continuous interaction. And when something breaks that pattern, you're expected to re-engage instantly and make a correct decision. So the effort isn't constant. It's intermittent, but concentrated. And as these environments become more complex, the situations you're stepping into tend to be harder to interpret, not easier.
Right, and from the outside, none of that is visible. It just looks like the system is running smoothly. So what's actually happening underneath that smooth surface?
Most of the time, the system is operating as designed. But that apparent smoothness depends on something that isn't always visible. When the system encounters a situation it doesn't fully understand, it doesn't resolve it the same way it handles normal operation. It hesitates, it pauses, it reaches a point where it no longer has a high confidence path forward. And in many implementations, that's where a person steps in. Not to run the process, but to interpret what's happening, make a judgment, and guide the system back into a state where it can continue. Those moments are relatively rare compared to total activity, but they're essential. They're what prevent the system from drifting or breaking under conditions it wasn't designed to handle independently.
Got it. So when people talk about full autonomy, they're mostly describing what's visible. What's getting missed in that picture?
What you see is the portion of the process that can be standardized and repeated reliably. And machines are extremely effective in that domain. But the environments these systems operate in aren't fully predictable. So instead of eliminating that unpredictability, the system is designed to operate up to a certain boundary. And beyond that boundary, something else has to take over. That's where the human layer sits, not as the primary driver of the process, but as the part that handles what can't be fully specified in advance. So autonomy in practice is partial and structured, not absolute.
Right, so it's less about replacing people and more about redefining where they sit within the system. And as these systems scale, what happens to that role?
The shift becomes more pronounced. The core of the process becomes more efficient, more stable, more automated. But the surrounding complexity doesn't disappear. If anything, it becomes more visible, because what's left is everything that doesn't fit neatly into the system structure. And that's where human involvement concentrates. Interpreting variation, resolving ambiguity, making decisions in situations that can't be fully reduced in advance. Not everywhere, but at the points where it matters most.
So the closer you look at these systems, the less it resembles a clean handoff from human to machine. It looks more like a redistribution of responsibility, where the predictable parts of the process are automated, and everything outside of that range is handled differently.
Exactly. The system isn't removing the human, it's reorganizing where the human sits within it. The stable portions of the process become highly efficient, highly repeatable, and largely self-sustaining. But the unpredictable portions don't disappear, they become concentrated, routed toward a layer that can interpret, adapt, and respond when the system reaches its limits. And that layer is still human.
Which explains why autonomy can feel more complete than it actually is. From the outside, the system appears seamless, but that smoothness depends on something that isn't always visible.
That's right. Most of the system runs without interruption. But that continuity often depends on a set of interventions that happen at the margins, moments where the system encounters something it can't fully resolve and requires guidance to continue. So the system works, but not entirely on its own. It works because its boundaries are actively managed.
And that shifts the framing again. Because now the story isn't just about autonomy increasing over time. It's about how that autonomy is supported.
Exactly. It's about how the system is stabilized, how it absorbs variation, how it handles ambiguity, and how it responds to situations that fall outside its model. Because those situations don't go away, they move. And in most real-world systems, they move toward the human layer, which means the defining question isn't whether the machine can operate independently, but how the system is designed to function when it can't.
With Volo, lending and borrowing is effortless. No spreadsheets. No awkward follow-ups. Volo automates everything, from repayments to reminders, so your lending feels effortless. Every payment is tracked, updated, and secured, with encryption protecting every transaction. Automate with peace of mind. Volo protects what matters, so you can focus on what's next. Join the waitlist today at voloapp.ca.
If you zoom out across everything we've talked about, there's a pattern that starts to come into focus. Not just about where AI works, but about why it stalls. Because at a distance, the trajectory still looks very clear. The systems are improving, the capabilities are expanding, the investment is there. And yet, when those systems move from demonstration into deployment, something slows down, sometimes dramatically, and it doesn't quite match the pace you'd expect.
Yeah, and I think what becomes clear is that the bottleneck isn't where most people assume it is. It's not primarily in the intelligence anymore. We've crossed a threshold there. The systems are capable enough to be useful across a wide range of domains. But usefulness in isolation is very different from usefulness inside a functioning system. Because real environments aren't just problems to be solved. They're systems that have to stay coordinated while the solution is being applied.
So it's not just whether the AI can do the task, it's whether everything around that task can adapt to it.
Exactly, and that's where integration becomes the real constraint, because for AI to work in the physical world at scale, it has to align with multiple layers at the same time. It has to fit into existing processes, it has to coordinate with human operators, it has to meet safety requirements, it has to synchronize with timing, logistics, infrastructure, and each of those layers has its own complexity, its own inertia, its own failure modes.
Which starts to explain why so many transformation efforts struggle to fully land, even when the underlying technology is strong.
Right. There's a well-documented pattern now where a large share of digital and AI transformation efforts never fully scale. They work in pilots, they show promise in controlled environments, but when you try to expand them into the full system, that's where friction shows up. Because scaling the model is relatively fast. Scaling the system around the model is not.
And that's a very different kind of problem. It's not a breakthrough problem, it's a coordination problem.
Yes, and coordination problems are inherently slower. They require alignment across people, processes, and infrastructure that were not originally designed for this kind of interaction. In many cases, you're not just adding intelligence to a system, you're asking the system to reorganize itself around that intelligence. And that reorganization takes time, sometimes years, because you're dealing with physical constraints, legacy systems, regulatory frameworks, human behavior, all of which move at very different speeds.
So when people see rapid progress in AI and then feel like the real world impact is lagging behind, this is where that gap comes from.
Exactly. It's the difference between modeling and integration. Modeling is fast. You can improve performance, train systems, iterate quickly. Integration is slow because you're not just improving a system, you're embedding it into a larger environment that has to continue functioning while the change happens. And that's a much more delicate process.
Which brings us back to something we've been circling throughout this series. Each episode has been pointing at a different constraint.
Yeah. If you think about it, episode 25 was really about the workflow constraint, how intelligence has to fit into how work actually gets done. Episode 26 moved into the infrastructure constraint, the physical and organizational systems that support that work. And here we're looking at the integration constraint, which is what happens when you try to bring those two things together, intelligence and reality inside the same system.
And that's where things get difficult. Not because the pieces don't exist, but because they don't naturally align.
Exactly. And I think that leads to a more grounded way of understanding what's happening right now. AI isn't failing because it lacks intelligence. In many cases, it's already capable enough to create real value. What it runs into is the complexity of the systems it's trying to become part of. Systems that were built over decades, optimized for different constraints, and not easily reconfigured.
So the limiting factor shifts again, from capability to compatibility.
Yes, and compatibility is harder because it's not something you can solve in isolation. It has to be negotiated across the entire system, across humans, machines, processes, and environments. And until that alignment happens, the intelligence remains partially unrealized. Not because it isn't there, but because it hasn't been fully integrated.
Which reframes the whole trajectory. It's not just about building smarter systems, it's about building systems that can actually absorb that intelligence.
Exactly. And that's a much longer process because it requires changing reality itself, not just the models we use to understand it.
So when we ask, where is this all going? The answer may be less about how far the technology can advance and more about how much of the world can adapt to it.
Yeah, because in the end, AI doesn't stall at the edge of intelligence. It stalls at the edge of integration. And that edge is defined by reality, not by the model.
And that might be the most important shift in perspective.
Because it forces a different kind of question, not just how we build more capable systems, but how we design environments that can actually work with them, how we align human judgment, physical processes, and machine intelligence in a way that holds together under real conditions. And that's not a single breakthrough. It's a gradual, ongoing process.
So the story isn't over. If anything, it's just moving into a different phase.
One where the challenge is no longer just intelligence, it's integration. And that's a much harder problem to solve. Because intelligence can be trained, but reality has to be reshaped.
That's it for the show. Like and subscribe wherever you get your podcasts, and reach out to us anytime at talk@torontotalks.ca. We'll see you next time right here on Toronto Talks, where big ideas come to life.
And curiosity never sleeps.